recording it to YouTube as well in the meantime. All right, so it's getting there. All right, that's awesome. And then let's go back here and then pause recording. Here we go. All right. So today we're going to start learning another application of the derivative concept. And it's mostly like determining the increasing, decreasing behavior of the function by just looking at the first derivative of the function. So in short, today we're going to try to achieve learning another application of hold on. Okay. So in short, today we're going to try to achieve how we can determine the intervals on which a function is increasing or decreasing without graphing, obviously. And how do we apply the first derivative test to find relative extrema of a function? Right? Because if you have an increasing, decreasing behavior, at some point, you should reach the peak and then you should start going down. Or if you're decreasing and then all of a sudden you start increasing, you should reach the deep, right? So that means you make a valley. So you should have a relative minimum. So we're going to sort of like bring these two concepts together, relative extrema and increasing, decreasing behaviors. Okay. All right. So first of all, let's make the definition of what it means to have an increasing or decreasing function. So first of all, f is an increasing function on an interval. Okay, for any for any two numbers x1 and x2, such that x1 is always on the left of x2, the corresponding function values would satisfy this relationship. So if x1 is on the left and x2 is on the right on the interval, so f of x1 should be less than, strictly less than f of x2 to call this function an increasing function. And likewise, f is a decreasing function on an interval. When you pick two numbers, x1 and x2, such that, again, x1 is on the left of x2, right? The corresponding function values would be satisfying f of x1 is less than f of x2. So let's say like f of x, oh, this is greater than, I'm sorry. This would be greater than, there's a typo here, okay? F of x1 is to be greater than f of x2. So if f of x1 is right here and f of x2 is here, so about this kind of function, okay, for a decreasing function. I'll have more examples anyway, but first of all, correct the typo here, that in the second definition here, this should be greater than sign. Make sure you have that, okay, and I'll correct it in my lecture notes. And here is a nice example, okay. So as you see that, you know, in the graph, you have all the increasing and decreasing behaviors all the way, but let's just try to read what the slide says. A function is increasing when a function is increasing when, as x moves to the right, its graph moves up. And it's decreasing, obviously, when its graph moves down. So as you see here, when you go in this direction, okay, in this interval, so this function is decreasing, and because the corresponding function values keep like increasing all the way, right? Whenever you hit a, right, x equals a, then you keep just going constant, okay, till when? Till x equals b, and then you go back up increasing, starting from x equals b. So when you go in this direction, in one case it's decreasing, in another case it's constant, and then in the next sub-interval it's increasing, okay? So when we look at these like increasing, decreasing behaviors, what can we say about the derivative of the function, okay? Well, the derivative of the function tells a lot, because when you have a decreasing function, see, like, check all the slopes at any point, right? Here, there's the tangent line. There's tangent line, right? Here's another point, its tangent line is like this. So what is the commonality between the slopes of tangent lines here? Well, these are all lines having negative slopes, right? So negative slopes. And here, any point you pick in this interval, well, you have the tangent lines all horizontal. So in fact, here slopes are 0 at any point, right? And whereas here, if you look at the tangent lines at any point, right, slopes are always positive because uh, these are increasing lines, and in this case, lines are decreasing here, right? So then you have the negative slopes, positive slopes, and 0 slope here. So you can see the relationship between increasing and decreasing behavior and the slopes of the function on those intervals. Okay. So this picture explains all, but I'm going to sort of like present this come in this fact. Okay, let's just check this fact here. This is theorem 4.5. Let's just read it quickly. Let's say I give a function continuous on the closed interval and differentiable on the open interval AB. Okay. Then what can we say about increasing, decreasing behavior by looking at the first derivative of the function? Okay, let's check. If f prime is positive for all x in the open interval AB, then we can conclude that f is increasing on the closed interval AB. If f prime, the sign of f prime is negative for all x in the open interval AB, then we can immediately conclude that f is decreasing on the closed interval AB. And if the derivative is 0 all the way, like this case here, 0 derivative all the way on this interval, then we can go ahead and conclude that f is constant on the closed interval AB. So essentially, this result is a summary of this nice graph here. Okay? Decreasing, then f prime is 0. I mean, f prime is 0, then it's decreasing. F prime is 0, then it's constant. F prime is positive, then the function is increasing. So essentially, this summarizes the graph and puts it as a fact. Okay. Any questions so far? If there is any question, hit yes or no. By using the participants feature. Okay, I'll see the yeses and nos. I have 10, 11 no's. All right, any question? All right. All right. Thank you. All right. So let's have an example just to apply this idea. So the question is asking, find open intervals on which f of x is increasing or decreasing. All right, let's check this. Well, to determine if f is increasing or decreasing, we should look at f prime. And then you have to ask this question to yourself, is f continuous, is f differentiable? Okay. Well, this is a polynomial function, and as you see that this function is, in fact, continuous and differentiable, then you can find f prime by using the power rule. That is 3x squared minus 3 halves times 2 times x, which is 3x. Okay. So once you have f prime, you can look at sine of f prime, right, on different intervals to determine the increasing and decreasing behavior. But to determine the sine of a function, in this case it's f prime, you have to look at the zeros of the function, right? So you want to know if the graph of f is about the x-axis or below the x-axis. So you need the x-intercepts, in other words. So to find that, you have to set this equal to 0 and see what the x-intercepts are for f prime. Okay? And to do that, you can pull x out, and in fact 3x out, because 3x is a common factor, right? This is x minus 1 equals 0. So this tells me that x equals 0 and x equals 1 are the two intercepts, x-intercepts. Okay. So at this moment, well, we know the x-intercept, but we need a sign chart. We need to know the sign of f prime on different intervals. So for that reason, I'm going to go ahead and then have a sign chart. Okay. So since x equals 0 and x equals 1 are the critical numbers, right? That's also telling us that since we solved f prime equals 0, whatever x comes out of that is a critical number. So we do have two critical numbers. I'm going to have my sign chart like this. Okay. And you can do the same thing by yourself. Okay? So here is the x-axis. So I'm going to put the critical numbers right here. Okay. And this part, when you go in this direction, you go to minus infinity. When you go in this direction, you go to plus infinity. Okay. So you can also put the plus and minus infinity. Okay. So now I'm going to look at the sign of f prime to deduce the increasing and decreasing behavior of f. Okay. To achieve that, what I'm going to do here is to get like sample points from each column. Okay. I'm going to pick sample points from each column. All right. So since we're in the interval, let's say minus infinity and 0 here, well, I'm going to choose a simple number like -1 here as my sample number. And here I'm going to choose 1/2, and here I'm going to choose 2. So we're picking one number from each interval. Okay. And next is to look at or to evaluate for this problem three things. One is f prime at -1. The one is f prime 1/2. And the last one is f prime 2. So we're looking at the signs of f prime, at those sample points. Okay. All right. So what was f prime? Let's go back here. Let's go back. F prime is 3x squared minus 3x. In other words, 3x times x minus 1. Let me just copy that down here. So f prime is 3x times, well, maybe that's not the best place to write. Hold on. I'll just write it here. F prime is 3x times x minus 1. Okay? All I need for these guys is just a sign of f prime. I don't need to know exactly what those numbers are, okay? But I just need to know the sign of those. In other words, I just need to know if these guys are positive or negative, okay? All right, let's check. So f prime at -1. So I'm going to go ahead and then put -1 for x and see, again, if f prime is going to be positive or negative. So when you look at -1 plugged in to f prime, so this guy is -1, right? And this guy is -1. So -2 times -3, that's going to be positive. It's +6. You can also use your calculator, by the way. So this is going to be for sure positive, okay? So now let's plug in 1/2 for x. Okay, so this part here is going to be 1/2 minus 1, so it's going to be negative, right? And this part here, 3 times x, is going to be positive. So positive number times a negative number is going to be just negative. Okay. So again, we're just checking the sign of f prime for those sample points. Okay. And finally, we're going to put 2 for x. Well, 2 minus 1 is positive. 3 times 2 is positive. Positive times positive is going to be positive. Okay. So once you determine the signs of f prime at the sample points, you can go ahead and write here, let's see, f prime at -1 is positive. I'm going to put a plus sign here, minus sign here, and plus sign here. Okay. So these are the signs of f prime at the corresponding interval. So by just checking the sign of f prime at -1, I can just tell that f prime is in fact positive on -infinity and 0, and it's negative on the interval 0 and 1, and positive on the interval 1 and infinity. Okay. So going back to this fact here, it says that if f prime is positive on an interval, then f has to increase, right? Or if f prime is negative on an interval, then f must decrease on that interval. So I'm going to go back here, and then I'm going to deduce increasing, decreasing behaviors on each subinterval by looking at those plus and minus signs. So since I have a plus sign here, I'm going to go ahead and say that f is increasing, and f is decreasing, and f is increasing here. Okay? Thanks so far. Hit yes or no, please. I need feedback because we're going to do this sign chart business all the way for each question for the rest of this chapter. So I want to make sure like we understand them all. Oh, you have a question. Okay. Whoever has a question, please. Oh, you don't have a question. Okay. All right. Somebody just yes and then took it back. So, okay. 11 no's at this moment. So you have no question. That's good. All right. So let me just put the slides writing of that because my handwriting may be like ugly at this moment. So I'm going to discard this and put the slides nice description of exactly what I did. Okay. So we have the test values, right? We determined the f prime all the way for each subinterval, and we said that f prime is positive here, negative here, positive here, and then we said it's increasing, decreasing, and increasing. You can also use this type of sign chart if that looks more fancy for you, but this is exactly the same as exactly what I did here. Okay. So and you can actually go ahead and then graph the function. Let's see, graph the function x cubed minus 3 halves x squared, and you can put the x min to be let's see, x min to be -1, x max to be 2, and make sure you get the same graph. So let's have a reality check. Well, first of all, on the interval -infinity and 0, right? On the interval, so this goes to -infinity. On the interval -infinity and 0, this function has to what? Has to increase. Here we go. I have a nice increasing function till when? Well, till you hit the critical point x equals 0, right? So you're going to keep increasing till you hit the critical point x equals 0. Then you start decreasing. Till when? Till x equals 1. Okay? So you starting from here, decreasing all the way to x equals 1 up here. Okay? Then the table says that you're going to start increasing all the way till infinity. So when x gets larger and larger, starting from x equals 1, you keep increasing all the way to infinity. Okay, so this is sort of like how you interpret table together with the graph of the function. Okay. All right. Any questions so far? I'll just clean this up. If not, I'm going to continue with more sort of like a guideline to determine the decreasing behavior. So let's say like you're going through a homework problem. So what guidelines you should follow? Okay, first thing is obviously check if f is continuous on the interval AB. And this could be like -infinity and infinity as well. So depending on what function is provided to you and what interval is provided to you. Okay. And so to determine increasing and decreasing behavior, first of all, locate the critical numbers of f. Okay, like in the previous example, we set f prime to 0 to get one type of the critical points, but you can also look at critical points of the second kind where f prime is not defined. But since we had a nice polynomial in the previous example, right, nice polynomial to start with, f prime is defined everywhere. See, f prime is this guy here. And we didn't need to worry about the critical point of the second kind, but for other types of problems, we're going to check the critical points, both kinds, okay? And then you're going to determine the sign of f prime at one test value in each of the intervals. And this one, you should take it as like have a sign table, like the one I had, or like the one the slide had. Have a sign table by placing the critical numbers in it. And then choose your test points from each subinterval and determine the sign of f prime based on that. Okay, and based on again the sign of f prime, deduce if f is increasing or decreasing. In other words, if f prime is positive on subinterval, then f is increasing. If f prime is negative, f is decreasing, and if f prime is 0, f must be constant on that corresponding subinterval. Okay, so take this as like a good sort of like guidelines to determine increasing and decreasing behavior. Here is just a quick definition. We call a function strictly monotonic on an interval when it's either increasing on the entire interval or decreasing on the entire interval. For example, the x cube function, f of x equals x cubed, if you just graph it all the way from minus infinity to infinity, you can see that it's strictly increasing, right? It's just keep increasing all the way. There's no instance or there's no sub-interval this function decreases. So for that reason, I can call this function a strictly monotonic function, and I can in fact say that it is a monotonically increasing function, okay? Whereas for this function, I can't really say it's monotonic because, well, this function is increasing, obviously, but on those intervals, like minus infinity and 0, and then 1, 1, all the way to infinity. But if you look at this interval here, right, 0 and 1, it's constant. So essentially, it's not increasing or decreasing at all. So that constant behavior prevents us calling this function a monotonic function. Okay, so for a function to be monotonic, it should strictly increase or decrease, whichever is applicable. Okay. All right, let's just keep going. So now, how are we going to connect this to relative extrema? Okay, like in the previous example, we found critical numbers to be like 0 and 1, right? 0 and 1 were the critical points. We determined the increasing and decreasing and increasing behavior through the subintervals. So what can we say about the relative extrema, like for this example? Well, since we have the graph here, we can sort of like comment on that. Well, you have this like all like nice increasing behavior till you hit 0, right? Till you hit 0, and then all of a sudden you start decreasing after. So then this point, since in fact it's a critical point, right? So at this point, in fact, f prime equals 0, right? So I have a relative maximum here, okay? And the same way, so you keep decreasing and decreasing and decreasing till you hit x equals 1. And then it turns back up and you start increasing. So we have another critical point here where f prime is equal to 0. Okay, so this tells me that you have a relative minimum at x equals 1. All right. And then you can go ahead and conclude that f is a relative minimum at the point 1 and negative 1/2, because f is decreasing immediately to the left of x equals 1 and increasing immediately to the right of x equals 1. And likewise, you know, 0, 0. At 0, 0, you have a relative maximum because on the left, it's increasing on the right, and it decreases immediately. Okay? And I'm going to put this in a statement here. It's called like first derivative test. And then you will see in the homework problems stating that use the first derivative test to determine the relative extrema of the given function on the given interval. So then you're going to sort of like remember this first derivative test. So let's see what it is talking about. Well, first of all, you start with a critical number. Okay, either of the first kind or the second kind, okay? And f is continuous on the interval where the critical point belongs to. And f is differentiable. It doesn't need to be differentiable at c, by the way, but it should be differentiable on the interval containing c, because c could be a second kind of critical point, which is essentially meaning that, you know, f prime is not defined. Right, like if you exclude c, then the function in the neighborhood should be differentiable. Okay? So this one says that if f prime changes from negative to positive, that means you have the decreasing behavior, and then increasing behavior immediately after you hit the critical point. So this c guy, the critical point c, should be a relative minimum, okay? And if f prime changes from positive to negative, here is a representative example. So you keep increasing and increasing and increasing and increasing, and you hit the critical point c, and then you start decreasing because f prime, the sign of f prime becomes negative across c, right? So that means you should have a relative max. Okay. If f prime does not change its sign across a critical point, like in this case, for example, right? F prime is positive because f is increasing, right? While f prime is still positive, f is still increasing, right? You can't say like this point, it gives you a relative extrema. There's another name for this point, but you will see that in the next chapter. And likewise, f is decreasing here all the way, right? F prime is negative for that reason. And then you hit the critical number, but you keep decreasing because f prime is negative, right? So this point is not a relative extrema, in other words, okay? So again, if f prime does not change its sign across a critical point, you can't really get any relative extrema out of that. Okay, so this is called the first derivative test. And when you have the sign chart, you're going to look at the change of the sign of f prime to pinpoint relative extrema. Okay. Let's have one more example to go with. And to apply this concept of like the first derivative test to pinpoint relative extrema. So the first question that we're going to check is for the function f of x equals 1/2 x minus sine x. And the interval is provided to us. So we're going to consider this function only on this interval. In other words, we're going to investigate increasing, decreasing behavior of the function only on this interval. And if you want, at this moment, you can go ahead and then graph this function for x min to be 0, x max to be 2 pi, and tell me what the graph of the function looks like. Because since you're allowed to use your calculator, that would give you some hints about the increasing and decreasing behavior by just simply graphing the function. So tell me what the graph looks like. Again, this is your x min, and this is your x max. Okay. So you should probably get something like this. I'll give you like 20 seconds to convince yourself. So you simply graph the function 1/2 x minus sine x. for x min to be 0, x max to be 2 pi. And then you have punches here because you are given an open interval, okay? So endpoints, in other words, not included, so endpoints cannot be considered for relative extrema. Right? If you're sort of like convinced yourself, you can go ahead and then look at f prime. All right, so what is f prime? Well, remember, we're trying to determine the critical points. Well, f prime in this case is 1/2 minus cosine x. Okay. There are two kinds of critical points, right? First and the second kind. And first kind is found by setting f prime to 0, and second kind is checking if there is any x for which f prime is not defined. Okay, let's look first critical point real quick. I'm going to set this to 0 and check what kind of like solution I should get for. So this gives us cosine x equals 1/2. Okay. And this is the best time to use the unit circle, by the way. So you want to know when cosine takes the value of 1/2 on the interval 0 and 2 pi. And the way you use the unit circle here is that you have like bunch of numbers here, right? Bunch of numbers, bunch of actually points on the unit circle, right? And cosine is always the x coordinate of those points. Okay? So since 1/2 is a known number in terms of cosine and sine, so you're going to look at the x coordinate of the points, x coordinates of the points for which the x coordinate is 1/2. Okay. So which points on the unit circle come with the x coordinate to be exactly 1/2? Who's going to unmute and tell me exactly what it is? On the unit circle, again, which points would spit out the x coordinate to be exactly 1/2? Who wants to speak up?
Is it pi over 3?
Pi over 3. Is that the only one?
5 pi over 3.
Yeah, so you have 2 points, right? Thank you. You have 2 points. One is this guy and the other one is this guy, right? For which the x coordinates are 1/2. Okay, so I can go back here. I can go back here. I can go back here, like x equals pi over 3 and x equals 5 pi over 3 are the only 2 candidates for which cosine of those would be 1/2. And why am I interested only these 2 points? Because we are in the interval 0 and 2 pi. So if this interval was larger, let's say like 0 to 4 pi, then I should have another revolution on the unit circle and then maybe grab more points. So what I'm trying to say is, like, if the interval was larger in the problem, then I would have another rotation here. So in other words, I would add 2 pi to those, right? 2 pi to those, so that I would grab 2 more points coming along if the interval was like 0 and 4 pi. Okay, and if the interval was involving negatives, then you would probably go clockwise. So you would add multiples of -2 pi to those pi over 3 and 5 pi over 3 to find other candidates for which cosine is 1/2. Okay, but since we're again on the interval 0 and 2 pi, these are the only 2 candidates for critical points. For the second type of critical points, we don't have any because we have 1/2 and minus cosine x defined everywhere. So I can go ahead and just say that, you know, there is no critical point of the second kind because f prime is defined for every x, and in particular, it's defined on the interval 0 and 2 pi. Okay. All right. So since I pinpointed the critical points, I can go ahead and then write down the sign chart. You can also use the table sign chart, which is perfectly fine. I'm going to use that one, in fact. Okay, so here you go. So I place the critical points right, pi over 3, 5, pi over 3. This is minus infinity. This is plus infinity, right? So now I have 3 subintervals to consider. One is this, the other one is this, and then this one is this. Last one is 5 pi over 3 and infinity. Okay. So I'm going to now pick sample points from each subinterval, okay? Or test values, whichever you want to call them, okay? So from the first subinterval, minus infinity and pi over 3, I'm going to pick pi over 4. From the interval pi over 3, 5 pi over 3, I'm going to pick pi. And from the interval 5 pi over 3 and infinity, I'm going to choose 7 pi over 4. You can also choose your own test values or sample points. It's totally up to you. So your test points could be totally different from my test points, which is fine. Okay. So in the next step, to determine the sign of f prime, we're going to look at f prime at pi over 4, f prime at pi, and f prime at 7 pi over 4. And who is f prime again? F prime is 1/2 minus cosine x. So put your calculator in the radian mode and try to calculate f prime at pi over 4, f prime at pi, and f prime at 7 pi over 4. So I'm going to cheat here from the slide that, f prime at pi over 4, which is in fact 1/2 minus cosine pi over 4. Go ahead and check that this is negative. And likewise, this is negative, this is positive. Okay? All right, so you can sort of like use your calculator to determine the signs of f prime. And again, I don't need to know exactly what f prime at pi over 4 or f prime at pi are. I just need the sign of f prime. That's it. I'm just checking if it is positive or negative. All right. So now by using the very first fact, if f prime is negative, then f is decreasing. If f prime is positive, f is increasing on the corresponding subinterval. So let me just clean this up a little bit. And I can go ahead and conclude that the f guy, is decreasing, increasing, and decreasing on the corresponding subintervals. Okay? So again, by looking at the sign of f prime, you deduce increasing and decreasing behavior for function f. That's exactly what we are doing here. Okay. So now, okay, this was the first fact that we used. So now I want to use the first derivative test. First derivative test to determine the relative extrema, if there is any. Okay. And for that one, here is the description. So if f prime is, let's say, changing from negative to positive, then we have a relative minimum. If f prime changes from positive to negative, we have a relative maximum. And if f prime doesn't change its sign through the critical point or across the critical point, so you can't really say any relative extrema behavior. Okay, so going back here, we have f prime negative, and it switches to positive here. So decreasing and decreasing, and then makes a turn, and it's increasing after that, right? So you should have a relative minimum here, right? You should have a relative minimum here. And likewise, you have increasing and increasing, and then start decreasing across 5 pi over 3. So you should probably hit a relative maximum value at the critical point 5 pi over 3. Okay? I should have this listed here, as I told you earlier. So this is pi over 3, and this is 5 pi over 3. Going back to the sign chart here, you're decreasing all the way till you hit the critical point critical point pi over 3, and then it turns back up, increasing. So you have a relative minimum at pi over 3. Going back to the graph, here we go. I have a relative minimum because I have a critical point where f prime is 0. I have a horizontal tangent line, and that's a relative minimum value. And at 5 pi over 3, you keep increasing and increasing, and then you start decreasing across the critical point. So we do have a relative maximum, and here we go. When you graph that, you have a horizontal tangent line at the critical point, and that critical point is in fact spits out a relative maximum value for the function f. Okay. Is there any questions so far? Go ahead and hit yes or no, because we have concluded the objectives of this lecture. So we first learned how to use the sign of f prime to deduce increasing or decreasing behavior of the function. And we applied the first derivative test to find the relative extrema, right? If f prime, the sign of f prime turns from positive to negative, it's a maximum. And if it's turning from negative to positive, that means we're talking about a relative minimum value. So we learned, in fact, two different things today. One is increasing, decreasing behavior, and the other one is how to come up with or how to pinpoint relative extrema by looking at the first derivative of the function. In fact, two things here are using f prime as like as an ingredient, because increasing, decreasing behavior, it means like you're looking at the sign of f prime, right? And for the first derivative test, you're looking at the critical points, which is again tied up to f prime. Okay. All right, so I see like there's no question as far as yes and no buttons go. Let me clean that up. There we go. Oops, not this one. Not this one. Sorry. So we continue with concavity and second derivative test. And by the way, if you want to solve more problems regarding 4.3, come back obviously during the recitation time tomorrow. And the TA is going to go over a bunch of 4.3 questions with you. So make sure you make it to the class tomorrow and don't miss it. And remember that we always share the links of the recorded videos with you. So if you can't watch the recitation live, make sure that you follow the links in Blackboard to watch them later. Okay. All right. So 4.4, this is another application of the derivatives. So this time we're going to sort of like pinpoint other behaviors of the function by looking at, in fact, second derivative of the function. One thing that we're going to deduce is the concavity of the function. So we're going to determine the concavity of the function. It's going to be either concave up or concave down based on the second derivative. We're going to sort of like pinpoint the points of inflection, which is essentially like you go up, 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 and all of a sudden you make a turn and you go keep going like up, up, up. So we're going to sort of like call this point an inflection point later on. And in addition to the first derivative test, we're going to use a second derivative test to pinpoint relative extrema correctly. Okay. And in fact, in the future, you will see that we're going to bring like first and second derivative tests together to accurately determine the relative extrema. Okay, but this section is sort of like devoted to the second derivative mostly, and then the previous section was more about the first derivative. Okay, so first of all, let's make the definition of concavity. Okay, So let's say like we have a differentiable function on an open interval. We say that f, the graph of f, is concave upward on that interval when f prime is increasing on that interval. So let me just clean this up a little bit. If f prime is, let's make this bigger. Right? If f prime is increasing on that interval, then we have concave upward. If f prime is decreasing, then we have concave downward. Okay, so this is what means to have the graph of a function to be concave up or down. And graph-wise, as you see that we have a differentiable function because we have the tangent line defined everywhere on the curve as you see from the graph, right? Here, f is concave upward because if you look at the tangent lines at different points, the slope is increasing, right? The slopes are increasing. So you have a negative slope here, you have a positive slope, you have a steeper line, so you have a bigger slope. If you go up, you will have the tangent lines to be like steeper. So as you move in this direction, essentially the tangent lines to the curve at different locations would have the tendency of being increasing all the way. So here f prime is increasing, okay? And the same thing applies for concave downward. And if you look at the tangent lines on the curve, so here, for example, you have f prime positive because this tangent line is an increasing type, right? Whereas here, the tangent line is a decreasing type, so f prime is negative. And f prime is even getting more negative because the tangent line gets like steeper if you just keep checking the tangent lines as you move in this direction for x's, okay? So that is a concave down behavior where f prime, again, is decreasing. So two things, f prime could be either increasing or f prime is decreasing to conclude that f is either concave upward or downward on the corresponding intervals. Okay. And here is the official description or official test to check for concavity without looking at the graph of the function. So all you need to know is the second derivative of the function, and you want to make sure that the second derivative exists on an open interval to determine the concavity of the function. So all you're going to look at is the sign of f double prime. If f double prime comes with a positive sign for all x, then the graph is concave up. Otherwise, if it comes with a negative sign for all x, then the graph of f is concave downward on the same interval. Okay, so again, we're checking the sign of f double prime to determine the concavity of the function. In the previous section, remember, we were checking the sign of f prime to determine if f is increasing or decreasing. So now this is a different situation. We're checking the sign of f double prime, right, on the corresponding subintervals to determine about the concavity of the function. Okay. All right, so you may run into the situation where f double prime is 0, and those are the ones, in fact, for us to check, or f double prime doesn't exist. These are sort of like, you don't call those like critical numbers, but these are like critical numbers, serving like critical numbers to determine the sign of f double prime on subintervals. Okay, so what we're going to do to locate those intervals, well, we're going to either solve f double prime of x equals 0, or we're going to check if there is any x that makes f double prime undefined. Okay. I'm just going to quickly go through this because we have only 5 minutes left. Okay, let's see if we can determine the concavity of this function. So remember that all we are interested at this moment is the second derivative of the function. Okay, so let's look at the first derivative. Okay. Well, this is an exponential function, so it's of the form e to the u, and the derivative of e to the u from the basic differentiation formula card, it's u prime times e to the u, right? So, well, u is negative x squared over 2, so the derivative of that is negative x times the exponential function itself. Okay, so I'm using this formula from the formula card of the differentiation rules. Okay? But I still need f double prime, so I should take the derivative of this function one more time. Let me use a different color here. But this time, it's not just exponential function, but it's the product of two functions. One is negative x, the other one is the exponential function. So we got to use the product rule. Okay. What is product rule? Well, keep the take the derivative of the first guy here. That's -1. And multiply it by the second. And keep the first one and take the derivative of the second. But I just took the derivative of that function, e to the minus x squared over 2, and I got minus x times e to the minus x squared over 2. Okay, so the derivative of this function already found by using this formula in the previous step. That's minus x e to the minus x squared 2. So now all I need to do is just simplify this. This is minus e to the minus x squared over 2 plus x squared e to the minus x squared over 2. And I can factor out e to the minus x squared over 2. And in the first term, I have -1. In the second term, I have x squared. And this is, in fact, f double prime. Okay. All right. So, well, I need to set f double prime to 0 and check if there is any x that makes this function undefined. So two things, right? Let me just go to the next slide, which is cleaner for you. So here we go. The description of what I just got and what I just wrote in the previous slide. So all I'm going to check if f prime is equal to 0 or f prime is not defined. Okay. But by looking at this is sort of like easier. Exponential function is never ever 0. So if there is any x that makes f double prime 0, these are the x's satisfying this, right? Because again, exponential guy is never ever 0. So that there's no way that that term could be 0. So this is non-zero. So I should solve x squared equals 1 to find the zeros. Here it is, x equals plus minus 1. And this exponential guy is defined for all x. X squared minus 1 is defined for all x. So we don't have this type of critical point. These are not critical points, but take it as like a critical point for now. We don't have this kind of x's satisfying f double prime not defined. Okay, so I have two values popping out of this. All right, so I'm going to put another sign chart here. Okay, here we go. I have -1 here. I have +1 here. I have -infinity plus infinity. And the deal is the same. I'm going to pick sample points. And this time I'm going to look at the sign of f double prime. From this interval, I choose -2, 0. And from this interval, I choose 2. And all I do is to check f double prime -2, f double prime 0, f double prime at 2. And this is sort of like something that you should check when you go home. F prime turns out to be positive here, negative here, positive here. And going back to the theorem and using the result, if f double prime is positive, you should have a concave up behavior or concave down behavior or concave up behavior here. And can we observe that in the graph? Yes, we can, right? Because on the interval -infinity and -1, the graph is like concave down, as you see. So concave up, I'm sorry. And between -1 and 1, it's concave up, as you see. And from 1 to 2, or from 1 to infinity, in fact, right, it's concave up. All right, so I'm going to stop here. But make sure like you sort of like calculate f double prime at the sample points and make sure like you got the same type of table. And I'm going to stop here. But before I stop, I would like to ask you if you have any questions. If yes, hit yes. If no, just hit no. And don't forget that I have an office hour today at 2 o'clock. If you still have questions, I can talk about this a little bit more during the office hour. Just let me know. I have 13 no's. That tells me that there is a no question.